So here finally is that force of gravity that we've been talking about. So Newton's universal law of gravitation goes like this, where the force of gravity that actually is a mutual attraction. So here we have two objects. We have the green object and the gold object. Notice that the green object is attracted or pulled to the gold object, and the gold object is also attracted then with the same force but in opposite direction to the green object. So that force that they're both feeling actually is mathematically equal to this, where G actually is a gravitational constant, but M1 is the mass of the green object, M2 is the mass of the gold object, and D raised to the second power D squared is the distance between them. So this is actually one of those that kind of makes sense, is that notice that if you increase the masses, then actually your force is going to increase. So that's why the force of gravity, for instance, on the moon is less than the force of gravity on the Earth. And the other thing is notice that if you increase the distance, okay, if you increase the distance, the fact that the distance is in the denominator is actually telling you that if you increase the distance, actually that's going to decrease the force. Increase the thing that you're dividing by, that will decrease the overall force. Kind of related to that is this idea of the force of gravity that's felt by an orbiting object. So remember we said that objects that are orbiting are actually under the influence of gravity. They're just like free falling and missing the Earth. So let's see. Okay, so here we have something in orbit, okay, successfully in orbit. Okay, it actually has a trajectory this way, the force of gravity this way, and so it kind of misses and ends up going this way. Okay, that's kind of how that works. So, but if the rocket were to have sufficient velocity, sufficient speed, it actually could have enough energy to escape the surface of the Earth. Okay, so this minimum energy needed to escape the gravitational influence of the object, or of an object, is called escape velocity. So I'm sure you buy this, the more massive, the more massive the object you're trying to get away from, then actually the stronger the force of gravity, the faster your escape velocity is going to be. Now, before we move on, remember though that Newton said that actually he had this r squared term, okay, in the force of gravity. M2. Now here's the deal. As this decreases, let's go ahead and make R decrease. As the R decreases, actually the force of gravity is going to increase. So here's the deal. What if our planet were actually smushed down and to a much smaller size? So all of the mass was actually squished down to a smaller size. Okay, so actually this object now in the middle here is going to be quite dense. Not only that, but if you now become a person standing on this object, okay, your radius is going to be a lot smaller. So your force of gravity is going to be a lot stronger. Not because the mass increased, but your radius got smaller. And actually this is what we approach when we talk about black holes and escape velocity. How fast do you need to be going to escape the influence of a black hole? Well, the force of gravity becomes stronger and stronger the closer you are to that mass, the center of mass.